Okay, so we're now going to look at the FOINA extension to the polynomials. There's a lot of crossover between the polynomials topic and the complex numbers topic, as you can appreciate. We've already done some factorising and what have you. So let's just, again, start off with looking at factorising complex expressions. And we've already seen this idea when we looked at complex numbers. We know that if all the coefficients are real, then the roots will be in conjugate pairs. And that allows us to create quadratics, and then we can factorise the polynomial. Now, every polynomial of degree n can be brought down to a mixture of quadratic and linear factors. So every polynomial can be factorised down to some combination of quadratic and linear factors. That's over the real field, because of course some quadratics won't factorise when we're just dealing with real numbers. But if we go further and use imaginary numbers, then it can just be broken up into n linear factors. So therefore, that logically means if you've got an odd-ordered polynomial, there must be at least one real solution in there. Because if the imaginary ones are appearing in pairs, you're always going to have an even number of imaginary solutions. Mm-hmm. That's right. We're talking about when the coefficients are real. Yeah. C is a very simple one, x squared plus 2x plus 2. But what I mentioned to you before is we could now use the idea of completing the square to factorise everything. And then use difference of 2 squares. Because we've got x plus 1 squared plus 1, doesn't look like the difference of 2 squares, but now we can say, oh, well, hang on, 1, that's the same as saying minus I squared, so we get x plus 1 plus I, x plus 1 minus I. So it gives us another technique to factorising. So every quadratic could be broken down to be the difference of 2 squares using completing the square on the algebra part. Z to the power of 4 plus z squared minus 12 equals 0. Noticing the powers are going up by a constant amount, so we could treat this like a quadratic. So z squared minus 3, z squared plus 4. Well, over the real field, that would be z plus root 3, z minus root 3, but z squared plus 4 doesn't factorise. If I was to keep going using complex numbers, then the z squared plus 4 could factorise. We have z plus 2i, z minus 2i. And thus our equations. Of course, reality is, if this is an equation, I probably wouldn't bother with those factorisations because I could go straight to saying, well, z squared equals 3 or z squared equals minus 4 and go from there. But if it was a factorisation question, obviously we'd go that way. Remember our factor theorem. If x minus a is a factor of a polynomial, then we know we can substitute a in and the answer should be 0. Because if it's a factor, it gives us a remainder of 0. And if it wasn't a monic, so I've got ax minus b, then I sub in b over a, so b over the coefficient of whatever x is. All right, let's try and factorise this one. It's a cubic, so I know there does exist a real solution. So I guess the idea is to try and find that real solution first. Well, 5's a prime number, so that makes life a little bit easier. So now I've just got to check 5 or 1, or minus 5 or minus 1. But it's not monic, so it could also be over 2. And of course, minus half is the first one you'd try. Well, it's only logical, really. Oh, look, it turns out to be 0. How lucky was I? So I now know 2x plus 1 is a factor. And then to get the other factor, you could either do it by polynomial division or just by inspection. You can create the other quadratic. Okay, that's over the real ones. Multiplies together give 5, adds together give minus 2. Not going to work. So we know the second one, I'd need to use complex numbers. So I'll complete the square. X minus 1 squared, but then it must be plus 4. So then I've got x minus 1 minus 2i, x minus 1 plus 2i. The other way I guess you could do that is x squared minus 2x plus 5. You could use your quadratic formula to work out what the solutions are and then go, okay, it's x minus 1 solution, x minus the other solution. Well, this particular polynomial, we know we have 2 rational zeros, which also means they must be real, okay, because you don't have rational and irrational imaginary ones. They're only real numbers. Find these zeros and then complete the factorisation using complex numbers, so over the complex field. Yes, again, logically a half would probably be the first one you'd choose there. No, of course it isn't. Prime number there's 3, so I'd probably be trying 1 or 3 first of all. They didn't work. So, oh well, it's probably a fraction divided by a factor of 4, so I could divide it by 4, I could divide it by 2. In this case, I've gone 1 over 2, eventually got my answer of equals 0. So I know 2x minus 1 is a factor. Mind you, the next one is a little bit more logical. If 2x minus 1 is a factor, logic sort of says to me the other real factor must be 2x minus or plus some number. Because remember, the imaginary ones are going to appear in conjugate pairs. And I know that when I expand it out, I'm going to get 4x to the power of 4. But I've already got a factor of 2x here. So I don't think there's going to be a 2x in the conjugate pair, because otherwise I get 2x times 2x times 2x. That would be 8x. So to me, logically, the other root, or the other rational one, is going to be over 2 as well. But let's see what we get. So let's factorise this one, leading term times leading term. So in the cubic, I get 2x cubed. The constant's got to be 3. Wonder what I did next. Worked out the x or the x squareds. I reckon I would have gone the x's. So we want 1x. At this stage, I've got 6x. So therefore, I need to subtract 5. So it would be minus 1 times 5x. Now we can go from the other end and work out the x cubes. Yeah, let's do the x cubes. I want 8x cubed. At this stage, I've got minus 2x cubed. So to get to 8x cubed, I'd have to add 10, wouldn't it? Add 10. So it'd be 2x times 5x squared. 5x squared. So there's our second polynomial. I guess rather than trying to find out what's another factor of 4x to the power of 4, etc., it's easier to work out what's a factor of 2x cubed plus 5x squared plus 5x plus 3. It's just a smaller thing to work with. Turns out minus 3 on 2 is the other one. So 2x plus 3 is the factor. So we found the rational zeros and hence complete the factorisation. So okay. Again, the constant will end up being 1 and x squared. I just need that middle term. How many x do we have at this stage? Sometimes you might find it easier to expand these two out to work out what the missing term is. We want 1x. At this stage, I've got 2x times 3 times 1. That's 6x. Then I've got minus 1 times 2x times 1. That's another minus 2x. So that's 4x I'm up to. I want 1x. So it's got to be, I think, do a little bit of maths over there, times what? It's simply 1x is what we need in there. Okay, well that one doesn't go over the real field, so I'll complete the square. X plus a half squared plus 3/4. There. Now this is really unusual because you'll see the fraction in there. But I've got to leave the fraction in there. If it was an equation, I could multiply and get rid of that fraction. But it's not. Remember, it's saying factorise this polynomial. So when I expand the whole thing out, I have to end up with 4x cubed. If I was to get rid of these fractions by multiplying both of them by 2, then when I expanded the whole thing out, I'd end up with 2x times 2x times 2x times 2x. It wouldn't be 4x cubed. So in fact, I have to leave that as a half plus root 3 on 2i and a half minus root 3 on 2i. As I say, if it's an equation, not a problem, because you can multiply the 0 on the other side and still make it a valid statement. Okay.